Hello everyone, this is a recording version of the webinar Unlocking Edge AI Advanced Features of Edge Impulse. My name is Louis Moreau. I lead the developer relation team with Edge Impulse, and I'm super excited to be here with you today. The main question we are going to try to answer, at least today, is how to scale your Edge AI pipeline to make it production ready. So we are going to see a couple of sections. The first one will be on the automation of your data pipeline. So how to aggregate data, how to validate or disqualify data samples, how to prepare, how to combine data together in order to create a ML-ready dataset. The second part will be around model optimization and how to build your projects. So we're going to see the difference between multi-impulse versus multi-model versus sensor fusion, how to extract features in a meaningful way, such as using neural network embeddings, how to develop and train your projects from your data using the Ion Tuner search spaces to constrain the hyperparameter searches. And I'm also going to tease you about the anomaly detection, especially our visual anomaly detection feature that is about to get released. And then in the end, we'll see what deployment options are available to you, what to choose depending on your machine learning journey, if you're in the test phase, if you're integrating your models, or if you want to scale and make it ready for production. Also have a special announcement to make. We are about to release an improvement of a super cool feature. Stay tuned and I'll let you know at the end of this webinar. Here is an example of one health wearable machine learning pipeline where the most important part, or where we provide the most value to our customers, is in the data pipeline automation. The model itself is important, but we notice with several of our customers, handling large-scale clinical studies was super tricky. So we developed a couple of features originally at Edge Impulse to answer this question. Then this is another example of a complete machine learning pipeline. It's more on the industry side. You can see that in the middle, in between your model development pipeline and your device pipeline, usually you have an aggregator, which is an IoT platform. And then your model can either live on a gateway, which is linked to different sensors, or it can be deployed directly on the machines on tiny sensors. First part, how to automate your data pipeline. So why it's important to automate the data pipeline? First, because you want to get gold standard labels, and this is super hard, and you want to catch error early. So if you manage your data pipeline right, it means like your model will be trained on data that are super relevant and are properly labeled, so your model will perform better over time. How to create that pipeline? So first step is to link a bucket. So basically it's any cloud-based storage. Usually it's done through buckets, and we support S3 compatible. So Amazon S3 is probably the most popular system to store data into buckets. We also work with a Google Cloud Storage or Azure options, or basically any S3 compatible. So to do that, you need to go to your organization in your data section, then create a data set. Add your parameters. Usually it means to fill the region, your bucket name, your credentials, secret, and API key. And once you've done that, you can create an organizational dataset, which differ from a project dataset. And this is what we are going to build. We have two options when we create organizational datasets. The first option is a default dataset, and the second one is a clinical dataset. So the name is probably not right because I'm using it a lot for other stuff than clinical studies. But the name is original because, as I said before, we develop those features around clinical studies. So the default view is a file-based one. It's super easy. It's like your Finder or your Windows file directory. You can drag and drop files in it, and you have a couple of actions to run transformation jobs on a dedicated directory or on some files directly. On the other hand, the second part is the clinical dataset, and here we provide more tools to help you to validate the data. So you have different filters if you want to navigate in it. You have some metadata, which are links to some checks, and those checks are super useful. The clinical dataset has 3 layers. So the dataset itself, it's a larger set of data items grouped together. The data item themselves, so you can consider a data item as a directory with more features, such as metadata and files attached to it. And then the files directly, so the files themselves that you can use and that can be transformed to create another dataset that is ML ready. Couple of examples of checklist, for example. So we have basic checks. Are all the files present? Do all the files start and around the same time? Are the expected labels present? But you can also do some more advanced checks, such as is there any correlation between a medical device and a wearable? So you can make sure the label you will add is actually according to the medical device. And again, the main idea is to catch errors early because data collection is super expensive in many use cases. So to create those checks, you can use transformation blocks. I'm going to cover that, how to use them or how to create them in a minute. I just wanted to show you an example of, for example, a data correlation, so validation examples on how to correlate data from a medical device. Here, if I'm not mistaken, it's a polar HR, so heart rates, and the PPG sensor. So if they are correlated, for example, on the left, you can validate the data and you can use it for your training. And if you have a scenario more like the right one, you may consider to disqualify the data sample, because if you're not certain, it might lead to errors while training the neural network. Once your dataset is validated, usually you need to parse it and make it ML ready. So in Edge Impulse organizational datasets, you can add any formats. However, when you want to use them in your projects, we only accept certain formats. It's the data acquisition format or the ingestion format in Edge Impulse. So we support JPEG or PNG images with or without bounding boxes. We support plenty of annotation formats, object detection annotation format. You can also import MPEG or AV video files. In that case, we can extract the frames to use them as images. We obviously support audio, for example, in our famous keyword spotting demos, or JSON or CBOR files, but these has to be in the right data acquisition formats. Same for CSV files. We support like kind of a strict format, but we also have another tool called the CSV wizard that you can use. And this will help you to parse your CSV. I'm not going to cover the CSV wizard in this webinar. Feel free to have a look at the documentation. It's super useful. And again, to transform your datasets, you can use transformation blocks to convert them and make them ready to be ingested in your Edge Impulse projects. What is a transformation block? So we use transformation blocks for several use cases. I'm going to cover that in a minute. Basically, a transformation block is a Docker container, either hosted, so a Docker image, either hosted on our infrastructures or Docker Hub, for example, which contains an application, so your script, your file, that can be written in any language. This is packaged in a Docker image, so the container itself. And then we add a couple of extra files or extra variables, such as if you want to use some parameters that your user can, or you can modify directly in the studio, and some things related to your organization and to your credentials. To push your transformation block, it's super easy. You can do with the Edge Impulse CLI Edge Impulse block init. It will initiate everything. And then to push it to our infrastructure, you can use Edge Impulse block push, and this will make it available directly in your organization. So how to interact with your data? So we have 3 main operating modes. The first one is a standalone mode. So no data is passed to the container, but you can still access the data if needed by mounting your buckets onto the container. I've seen some of my coworkers using the standalone mode for example, synthetic dataset creation or dataset augmentation. In that case, you may want to call directly the OpenAI API to generate synthetic data using DALL-E or other tools. Second mode is the data item level. So we pass the in directory and the out directory argument. So within a directory, you can merge different files together, you can transfer them. And the transformation job in that case will run on each directory. And then the third mode is on the file level itself. So we pass the file and the out directory, and the transformation job will run on each files present in your selected path. This is super useful. I've prepared a couple of examples in this GitHub repository. So those are mostly using CSV data, but we are planning to add some more over time as the usage comes. You can have a look at it. These are directly hosted on Docker Hub image registry, so you could eventually directly import them into your organization by just referencing the Docker Hub and the image tag when you will want to import a transformation block. Now that you have set everything together, so the validation, the data transformation, you can stack all those transformation jobs together in order to create data pipelines. So you can do that. So the data pipelines can run at a set interval every day, every hour, every week, or directly on demand. It can also be triggered through API. You can fetch data, combine them, parse them automatically, and also import them into an Edge Impulse project that you can automatically retrain as well. And then your dataset is now ready to be trained. And this is the end of the first section on how to automate your data pipelines. If you have any questions, feel free to ask them. We can also do a follow-up on forum.edgeimpulse.com. We spend on the developer relation team plenty of time on the forum to help you with your questions. You might have noticed this is a view that you might not be familiar with. The preview on the right is using some multi-label, so a feature called multi-label, which is super useful if you want to see, for example, a full clinical study or a full machinery state where you can add multiple labels, which is on the white graph. And this is actually the labels. That's it. I just wanted to mention that. Now, I hope you're ready to see some cool things on how to build and optimize your machine learning models. With Edge Impulse, we try to provide an Edge AI first approach and make your models hardware aware. So first, I'd like to give you three main concepts explanation. First one is on multimodal versus sensor fusion versus multi-impulse. I'm just going to go over quickly the definitions. So running multi-impulse refers to running two separate projects, different data, different DSP blocks, and different models on the same target. So basically running two projects. Running multi-modals refers to running two different models, so same data, same DSP, but a different TensorFlow or at least machine learning model on the same target. For example, if you run a motion classifier model and you add on top an anomaly detection model, those two will run on the same device. And then sensor fusion refers to the process of combining different data from different types of sensors to give the neural network more information, so to learn more effectively on different use cases. Here's a quick graph to explain you the three main concepts. First one is the multi-impulse, where you actually see two different projects then merged together. The one in the middle, the multimodal, so you use the same data, you use the same DSP, but you use two different learning blocks that you combine together in the same export package. This workflow is pretty straightforward with Edge Impulse, at least when it comes to a classifier and an anomaly detection model. And the third one can be straightforward in Edge Impulse Studio, or it can be pretty complex. We are going to see that in a minute, especially if you want to use neural networks embeddings. So you have two different kind of sensors, let's say audio and motion. And then you use one DSP block for one kind of sensor and one DSP block for another kind of sensor. And then you merge the output of them together in the same learning block to give your neural network more information. And then you combine that in the same export package. So I've got a full tutorials on how to do advanced sensor fusion using neural network embeddings. I'm going to go pretty quickly about this because it can be complex, and we can help you to automate those steps if you need at some point. So the default approach to basically use two DSP blocks that are available. So when using separate DSP blocks, you're constrained to the choice of neural network. So the features extracted from each data types can be fundamentally different. For example, a pixel in an image or a spectrogram and a data point from an accelerometer has basically nothing to do. They have distinct characteristics. So this incompatibility makes it challenging sometimes to use convolutional neural networks, which we know are pretty effective when it comes to extracting information from a spectrogram or from images. So as a result, if you use this standard or default approach, you may only be able to use fully connected networks in your learning blocks. So this process is not ideal, so that's why we came up with an approach using neural networks embeddings. And we use neural networks embedding in different places of the studio, in the Data Explorer, for example, in the auto labeling tool. So basically how this works, I'm going to take this example of a spectrogram. So you have as input the spectrogram. Then you have a couple of layers that can be convolutional. And then if you cut at some point the neural network, instead of having a classifier, or usually using a softmax layer, we cut it somewhere in the end and you obtain embeddings. So those embeddings can be used as features. So each layer of the neural network will start acting like a feature extractor, but will be highly tuned for your data. So you can combine your DSP techniques for extracting the spectrogram from audio, then add neural network architecture that you cut to extract the embeddings, and you can package that into one single DSP block, one custom DSP block. How to do that in EdgeImpulse? So first you need to prepare your data set. So you need to merge your data together to have one data sample that contains all your sensors. Then you need to train a first project only on your high dimensional data, for example, the audio. Then you can download the model generated from your trained impulse and eventually some test data as well that we can use to quantize your model. So this will be representative data of your data set. Then we put together an example directory on how to do advanced sensor fusion using neural network embeddings. We provide a script to cut the neural network at the end. I'm not sure if you see properly, but this is the default output of the save model. And here, after it's been passed to the save model to embeddings, we actually cut it so you obtain the embeddings. Once you've got this, you can pass that or encapsulate your DSP plus your cut neural network in a custom DSP block, push it as you would do with the transformation blocks. So EdgeImpulse block init, EdgeImpulse block push, and then it's available in your project. Then you need to create a second project to combine the two together and train it. Finally, you need to modify slightly the exported C++ library. You need to compile it with the Eon compiler. It can work with the default TensorFlow Lite. The modification that we need to make can be different, so it's not covered in the tutorial. And then you can compile and run the application, and you have more information to feed to the neural network, so the predictions will be very likely more accurate. You can see the full tutorial. This can be a bit tricky, so if you need help, feel free to reach out. Our solution engineers can help you on automating those steps to create your custom DSP block, to create a custom deployment block to automate those flow, and this can be directly integrated in your pipeline. I'll give you an example on the multi-impulse. So here it's only the simple way that I'm going to show you. If you want to see the hardcore way, how to merge all the files together in the exported C++ library, feel free to scan this QR code and go to the tutorial. We've automated all those steps into one custom deployment block, which is available then in your organization. And you can just add your two API keys of your two distinguished projects and directly obtain a C++ library that is ready to be run. For example, with this one, the project example I think I did was if we hear a glass breaking, then we run another model to detect using a camera if there is a person or not. That can be used for a security camera, for example. This is super cool. It's a tough thing to do manually to merge all the files together. And our coworkers, Aurélien, managed to create a custom deployment block, so it makes our life way easier. That being said, this is only needed if you need to run the C++ library. If you're using the Linux tools, it's way more easy. You can just instantiate two Edge Impulse runners with two different projects, and you can use them easily. And final thing, so the multi-model. So I'm going to cover the anomaly detection use case. It can work standalone or on top of a classifier, so thus the multi-model. How the anomaly detection work? Basically, we study the distance of an input based to different clusters. So if an input is inside a cluster, it means that there is no anomaly, and the further away is your unseen input, then the higher the anomaly score will be. How this works in reality, so we use some inputs to train the neural network, then we extract some meaningful features. Then we use clustering algorithms, for example, k-means or GMM, Gaussian mixture models. These usually work great with low dimensional data because those clustering algorithms use some classical ML instead of deep neural networks that can perform better with high dimensional data. But we've managed to create a feature, a visual anomaly detection. So it's not ready yet, but it's about to get released in a couple of weeks. Stay tuned. And we got inspired from FOMO. So basically how we do that, we remove the classification head and we replace it with some Gaussian mixture models. We only require to train it with normal data, or nominal data, and each cell tell you the chance if there is an anomaly or not. It has the same performances as FOMO, so up to 30 frames per second on a Cortex-M7, and it stays with less than 200 kilobytes of RAM. Here on the video, you can see that the model has been trained with those white rectangles, and if you add something else, it will highlight the part where is an anomaly. I've got two other projects that I used. Here it's a BinTech dataset where all the nominal data that you can see on the left, you can see a distinguished pattern. And if, for example, on the right, you can see something that is outside this pattern, we highlight it as an anomaly. Another example, which will be probably easier to understand, for example, with this piece of machinery, we only train with data similar to the one on the left. And when we pass for the inference data in the middle, you can see there is a kind of an impact on the top. So we highlight it in the anomaly scores. Same for the piece on the right, which is more completely defective. We highlight all the parts where we can see some defects. So this is super cool. I'm looking forward to see projects using visual anomaly detection from the community. This is great and has a lot of industrial use cases. Cool. And now the Eon Tuner. So maybe you're familiar already with our Eon Tuner. If not, it's our AutoML tool, but not only AutoML tool plus Auto DSP while being hardware aware. It's a super cool that we released, I think a couple of years ago already. And for those who don't know how it works, basically we test plenty of different variation of machine learning or combination of DSP and machine learning models in parallel, different jobs. And then we provide a grid with some models. You can choose between I want the model which has the best validation accuracy or the best testing accuracy. You can set your constraint. For example, I want this model to run within 500 milliseconds, or I want this model to use less than 50 kilobytes of RAM. So this is great. However, at some point you might be constrained either by your customers, your expertise, or the hardware that you already have. Let's take a couple of examples that I noted here in the slides. If your project requires to use a grayscale camera because you already purchased the hardware, you might need to constrain the search space of the Eon Tuner, not to search for RGB models. Or your engineers have spent hours working on a dedicated signal processing method and it's been proven to work. In that case, you want to use that and open up the grid search only for the neural network. Or basically, if you have the feeling that a particular neural network architecture will be more suited for your project because you've got great data scientists and they've got usually great expertise, in that case, you want to fix this one and open up maybe more other hyperparameters or the DSP or the signal processing part. How this works, you can use templates to do that. So blank template will look like the following. So you have some input blocks, DSP blocks, and learn blocks. If you don't know how to start, I recommend training first an impulse and then loading a template. We have pre-made ones, but you can start with your own project. So just load your own impulse and you will see all the parameters that you can change. Each element inside an array is considered as a parameter. So this means you can stack several combinations of input block, DSP block, and learn block. And in your template, each block can contain several parameters or several elements. This is super cool. I'm not sure if you had the chance to test this already, but if not, just try it for your next project. You can see it saves a lot of time. So that's it for the second part. Now we are going to see the deployment options. So for the deployment options, Edge Impulse models can be deployed basically anywhere where it supports C++. And you can deploy hardware optimized model to almost any devices or edge devices, gateways, or even using Docker container. Here is an example of different deployment options that you can have: smart cameras, gateways, sensors, directly health wearables. Not mistaken if I'm saying that I think we support the largest ecosystem of silicon vendors that works the same way with our tool. This is great. Depending on where you are with your journey, you might consider different deployment options. So if you're just evaluating Edge Impulse, this is something I've not even mentioned, but you can use your laptop or your smartphone just to test your models. This is super easy to do. Then if you're quick prototyping and evaluating the model on a dedicated chip, one easy thing to do is to use Edge Impulse firmware. So make sure you find a development board that supports the Edge Impulse official firmwares. We have plenty available, and these include hardware acceleration, and they also include sensor sampling. So you don't have to go through the sensor sampling strategy. The output of Edge Impulse Studio is just a binary that you can flash to your board, and within one command, just test your models. It's not super easy to modify this Edge Impulse firmware, but at least you can get some decent first results that prove the value of it. That's if you're on the MCU side. If you're on Linux-based devices, just use Edge Impulse CLI. Within one command, you can download your model, test it. We also support audio or images, depending on the hardware architecture you're on. If it's x86, Arch64, ARMv7, or even macOS, we leverage hardware acceleration. One good practice is usually as well to use Docker. In the Docker deployment options, you have a web-based app that where you can test your inference as well. This is super easy. Basically how it works, it's a wrapper around our .eem, which is our Edge Impulse model format for Linux. So this is super easy. Now, if you tested, you're happy with it, you might want to go through a custom implementation. In that case, you can use on the MCU side either our C++ library or any of the silicon vendor available libraries or export package. I can think of SLCC for Silicon Lab or for Silicon Simplicity Studio component. ER, Kyle that we just released. These are great packages to help you integrate with your existing application. They include hardware acceleration when possible. We provide documentation, and we also provide a standalone example on how to integrate that, or at least to run the inference using code, so that then you can integrate that in a broader application. On the Linux side, you can use the .aem plus our Linux inferencing SDK. So we have some available in Python, Node.js, C++, or even Go. I've never tried this one, actually. We also include the hardware acceleration, we include documentation, and we provide examples on how to do that. I've been adding a couple of Python examples. It's super easy to use. And then if you're happy with your integration and you're ready to deploy it and to launch your edge AI models to the market, usually one good option is to use the custom deployment blocks. So you can package everything together, and the output of Edge Impulse will be either a binary, a package that you can integrate in your fleet management system. That's available both for Linux-based application or on MCU-based ones. And on Linux, you can also use Docker, which is usually a good process to run containerized workloads. This is cool, and that's only the deployment option. Now, how can you optimize it even further? I'm super excited to announce that we're releasing today an involvement or an improvement, our Ion compiler, which is called Ion Compiler RAM Optimized. You will see that pretty soon, if not already, in Edge Impulse Studio. So you can select different optimization options. So whether you're just using the TensorFlow Lite, so the default deployment option, or the former Ion compiler, which is now called the Ion Compiler Latency Optimized. Or if you want to reduce your RAM, you can use the Ion Compiler RAM Optimized. Why we did that? Because we noticed that most of our customers are RAM constrained. Indeed, like the less RAM you have, the smaller MCUs you have, then you save cost on your bill of materials. And how it works, so by analyzing our machine learning architectures, we identified that most of the RAM usage was actually used to store intermediate results, especially in convolutional neural networks. So inspired by this, so we put together a method to compute the values directly as required, then minimizing the need to store these intermediate results. So by using this approach, we kind of trade off a higher latency with some substantial RAM saving. This is great. You can see here, for example, this benchmark has been done using MobileNet V2. So the RAM usage with the Ion compiler latency optimized is 2.4 megabytes. And the one with the Ion compiler RAM optimized is 951 kilobytes. And as you can see, you have a slightly trade-off for the latency. But if you want to save cost on your BOM, this might be a good way to go. Thanks a lot. If you have any questions, I will be super happy to answer them. You can go to forum.edgeimpulse.com to ask any of your questions, or you can also find all the tutorials that we've shown today on docs.edgeimpulse.com. Thanks a lot, and I wish you a pleasant day. This was Louis from the Developer Relations team at Edge Impulse. Thank you.